In this video, we're going to learn about a very popular algorithm called KNN, short for K nearest neighbors. This algorithm is quite popular and very easy to understand. We're going to learn about this using an example dataset. In this dataset that you see on the slide, there are only two features, number of years in school and height, and the label is whether someone is an adult or child. You also see here is a red dot on the slide. Whenever a row in the table is adult, it's represented by a red dot. And whenever a row is a child, it's represented by a green dot. Why are we color coding these two classes? It's so that we can plot this data and get a visual sense of how the data looks in a plot. Here is a plot of the data. On x-axis, you have number of years of school, and on y-axis, you have height. Here is how you read a plot. Let's pick the first row, where years in school is 0 and height is 2.18. X-axis is years in school, which is 0. 0 is over here, and height is 2.18, which is approximately somewhere over here. So this point represents this sample. Now, why is this point green? Why not red? This point is green because the label for this particular sample is a child, and child is represented by green color. Therefore, all the red points that you're seeing here are adults, and all the green points here are child. By just looking at the plot, you can see that if the height is a small number, then most likely it's a child. But then there is this area where someone could be a child or an adult. Also, if your years in school is a large number, then you're most likely an adult, even if the height is a small number. This is the kind of visual insight that plotting the data gives us. Why are we looking at this plot? Looking at a plot is a very easy way to explain the K nearest neighbors algorithm. Here is how the K nearest neighbors algorithm works. It first looks at this training data provided, which is what we are seeing here in the plot. It memorizes this training data and uses that to make future predictions. For example, you want the KNN algorithm to make a prediction on whether someone is an adult or a child, like the new point shown in the slides. Here's how it works. First, examine the values of this new point. If I project it down, years in school is somewhere around 6. The height, which you can project this way, is somewhere around 5. So years in school is 6 and height is around 5 feet. And if you plot the point, this is where the point falls in the plot. Now, the reason this is not colored is that we don't know if it's an adult or a child. That's for the AI to figure out. K nearest neighbors figures it out by looking at its neighbors. Who are the neighbors to this point? Which point do you think is the closest point to this? Looks like it will be one of these two, probably this one. Turns out that's the closest point. If I look at only one neighbor, my closest neighbor is red. KNN looks at who the neighbors are and predicts whatever the label of the neighbor is. In this case, it's an adult. K here is a variable. We looked at what the prediction is when K equals 1. Let's look at what the prediction will be if K equals 3. These are the three closest neighbors, and as you can see, 2 of them are green and 1 of them is red. The algorithm takes majority voting, and since 2 neighbors have the label child, this point is predicted to be a child. So what we see here is if K is equal to 1, it's predicted red, and if K is equal to 3, it's predicted to be green. What this tells us is that in a K nearest neighbors algorithm, depending on the value of K that you choose, your algorithm may predict an adult or a child in this case. What is a good value of K? Well, that's a little bit hard to answer. Before we get to that, let's look at another data set, which is a little bit different from this. Here is a regression data set. A data set is regression when what you're trying to predict is a continuous number. For example, in this case, what we are trying to predict is the price of a house. And price of a house is a number, it's not a category. Price could be any number, and hence it's a regression problem. Plotting a regression data set is a little bit tricky. It's not like classification where you can just say that adult is red and child is green. We cannot use different colors for different values because that will be too many colors and it's quite confusing. A good way to plot for a case like this is to give every point a number. There is no color coding, but every point has a unique number. But what does this number represent? This number is the index that you're seeing in the table here. This table is much bigger than the previous one because you have a new column called an index, which is here simply to identify the sample. It's not a feature. The features are square footage of the house and the age of the house. And what the AI is trying to predict is the price of the house. We have 10 points and every point represents each sample over here. KNN follows exactly the same principles that it followed in classification. If a new house comes in, which is around 600 square feet and 28 years old, how does AI predict this value? If the value of K is 3, it is going to look at who the nearest neighbors are. Here it turns out that 7, 8, and 9 are the nearest neighbors, which are these houses, 7, 8, and 9. And you can see that this is their label and their different values. So what should the price of this house be? In the real world, it turns out that there are several different ways to do this. A really simple way is to take the average. So let's take the average of the 7th house, the 8th house, the 9th house, and that's the price of my new house. So these are the ways that an AI predicts in case of KNN for classification and regression. Let's go back to the question of how do you find the best K? The process of finding the best K is called hyperparameter tuning. It's very hard to give a value as an answer. Every data set is unique, and you have to find out by simply trying out different values. It's something to experiment and find out. Whichever value gives you the best performance is the best K for the data set. In this process of figuring this out, where you change the value of K and keep checking how well your algorithm is performing, is called hyperparameter tuning. In summary, KNN is a very simple algorithm and is very easy to understand. It has a single parameter called K that you want to tune. As you learn about other algorithms, you're going to see that some sophisticated algorithms can have many hyperparameters to tune and can be very complex. But KNN has the advantage of being really simple, easy to understand, and easy to do hyperparameter tuning on. Let's do a small exercise to understand better how KNN works. Here is a table where you have 3 houses. House 1 is 1,000 square feet and 0 years old. House 2 is 800 square feet and 8 and 0 years old. House 3 is 1,000 square feet and 100 years old. You also have the label value, which is the price of the house. House number 2 is $10,000 and house number 3 is $5,000. As a human, if you were to predict the price of house 1 and you have only 2 options to pick from, either $10,000 or $5,000, what would you pick? Intuitively, I would pick house number 2 because this is a brand new house. It's 1,000 square feet. It should be at least $10,000. Let's think about what KNN would pick. If K is equal to 1, what is the closest neighbor? Neighbor or distance here is not in terms of how far the houses are from each other. It's in terms of the features, which is square footage and age here. In terms of square footage and age, which house is closer to 1? Is it 2 or is it 3? It turns out that distance between house 1 and house 2 is 200. The distance between house 1 and house 3 is only 100. But we know that a house that is 100 years old is actually pretty cheap compared to a house which is brand new. So the age of a house is much more important than the square footage. If you look at the difference in numbers, one would prefer this house instead of this one because age matters more. However, KNN completely misses this. The reason it misses it is it does not know that square footage is more important or less important than age. It rates all features equally. However, square footage can be anywhere from like 800 to 3,000, but age can only be between 0 to 200. People usually do not live in a 1,000-year-old house. Usually you see houses between 0 and 200. Square footage, on the other hand, you may see from 800 to like 3,000. Clearly the scale is different. You don't find houses which are like 100 square foot, right? And you don't find houses which are like 1,000 or 3,000 years old either. So the numbers start differently. Square footage does not start at 0, but age starts at 0. Starting point of these features is also different. In addition, the age is also different. As a result, KNN can sometimes give you really bad results because it does not know which feature to give a lot of importance to. This is a drawback of KNN to keep in mind. If you have an awesome data set and you think the AI is supposed to do really well, but it is giving you all kinds of bad predictions, then think about whether the features in your data set have different scales. What can we do to avoid this? There are a lot of things that researchers have done to make sure that we can directly tell KNN that one feature is more important than the other. Think a little bit about it and see if you can come up with some ideas. One really easy way to do this, multiply all values of age with 1000. Then the value of age becomes between 0 and 200,000. So you're artificially increasing the range of age. Alternatively, you could divide all the values of square feet by a constant number to make sure that they are more or less equal in range. This is one example of how the drawback of KNN can be overcome. Thank you.